Hello, everyone. Today I'll be talking about robust recovery and stochastic block models. This is joint work with Siddhant Mohanty and my advisor, Prasad Raghavendra. So today we're going to be talking about statistical inference, and for those who are familiar with the area, this type of phase diagram might be super familiar, but for those who aren't as familiar, I'll try to explain what this is at a high level. So inference problems are situations where I want to recover some information about the world given some data that I've observed. Super generic setup. But at a high level, a lot of these problems, at least in the TCS setting, can be parameterized by an appropriately defined signal-to-noise ratio, or SNR. And as you increase the SNR, the problem goes from being information theoretically impossible to computationally hard, and then finally to being computationally easy, where we have efficient algorithms. So a motivating question is, how sensitive is this phase diagram actually to differences in the modeling assumptions? So as a concrete problem that we'll use to study this question is we're going to study the stochastic block model. So the stochastic block model is quite simple to define, but it actually contains a rich phenomenology. Okay, so what is the stochastic block model, or SBM? So it's so to define it, I'm first going to sample a partition X, or you think of it as a hypercube vector. It's this hidden partition or signal, and I want to eventually recover X. Okay, and the data I'm going to observe is a graph G, which you can think of as a noisy observation of X. The graph G is going to have average degree D and signal strength lambda, and it's going to be generated according to this process conditioned on the hidden partition X. Okay, so the edges are going to be conditionally independent. I'm going to observe this graph G, and I want to, my goal is going to be recover X, just given G. You can think of this as being a version of Planet 2 XOR. Okay, and more relaxed goal might be to actually just output some estimate X hat, which non-trivially correlates with X. Note that this is an inference problem. It's not an optimization problem. If you try to do optimization, maybe you try to do maximum likelihood. Well, it turns out that the maximum likelihood estimate, i.e. min bisection, unclear if it's actually correlated with the ground truth X in the settings that we care about, which is a constant average degree and relatively low signal strength. Okay, just to restate our goal, we want to output some reasonably correlated estimate. So the question is, when can we actually do this? And people have studied this for a long time. And this picture, this phase diagram or landscape for the difficulty of doing this inference problem for at least a 2 community setting was conjectured to look like this. So the SNR is going to be lambda squared for us. And there was conjectured to be this transition at lambda squared equals 1 from being impossible to computationally easy. And this was conjectured by some physicists, Desel, Persikala, Moore, Zdevarova, and it was proven rigorously later by Moselny, Mensai, and Masselier. And for at least the greater than 5 community setting, there's also this intermediate conjectured computationally hard regime. And that computational threshold where it becomes computationally easy is known as the Kestensteigum or KS threshold. Okay, but today, just for simplicity, we're going to focus on the 2 community case. Our results will apply to the general constant number of community case. And just a reminder, in the 2 community case, the KS threshold is actually just lambda squared equals 1. That helps. Okay, so let's review some of the previous algorithms that actually were able to achieve this KS threshold. And at a high level, a lot of these algorithms are actually based on the so-called long walk statistics. So what are those? At a high level, this just means I take every pair of vertices in my graph, and I'm just going to count the number of walks of length log n. And one observation about these types of statistics is that, and algorithms, is that they're actually very sensitive to small changes in the graph. Like if I add some small cycles or cliques, then it's really going to mess up these statistics. And so given this observation, a very natural question might be, how specialized are these is this KS threshold to the exact modeling assumptions of the stochastic block model? So given this, a fairly natural way to get at this question of brittleness of the KS threshold is to relax the actual modeling assumption. And to do that, we allow an adversary to corrupt the graph. We're just going to be talking about edge corruptions in this talk. And for what is an edge corruption model? So in the edge corruption model, I give the adversary some budget delta, which is omega 1, and the adversary is allowed to arbitrarily add or remove delta n edges. The adversary can know what the true partition is, it sees the graph, you can modify it. Okay, so starting with this graph G, the adversary can come in and add and delete some edges, and only then is my algorithm able to see the input, this corrupted input, and try to recover the hidden partition X. I will note that there are some other SVM corruption models that have been studied in the literature, and just to briefly go over those, one of these is node corruption, where instead of modifying edges, I allow the adversary to modify any neighborhood of delta n vertices. It turns out that in this constant average degree setting, we can actually reduce it to edge corruptions. There's also the notion of a monotone adversary, which can only add edges within communities and delete edges between. And it turns out that this does, in fact, change the chaos threshold. But it sort of, because of this fact, that sort of looks at a different SNR regime than the one we consider. So it's incomparable. OK, so the main algorithmic result is the following. So first, let's define formally what we mean by robust recovery in the title. So we're given so let's say the setting is we have this clean sample from the SVM distribution, and I give the adversary some budget delta, and there's some target correlation rho. Okay, rho is omega 1 as well. The algorithm only sees G tilde, which is a corruption of G on at most delta n edges. And the goal of the algorithm is to output some estimate X hat, which achieves non-trivial correlation measured by rho. And so the main result in this area was due to Ding, Dorsey, Nasser, and Stoyer from 2021. And there they gave an efficient STP algorithm which succeeds at robust recovery for two communities. And the main result of our paper is actually an efficient spectral algorithm rather than an STP algorithm, which succeeds for any constant number of communities and also greatly simplifies the analysis of the previous paper. So let me just go over the plan for the rest of the talk briefly, and then we'll dive right in. So first, I'm going to talk about a new spectral algorithm for non-robust recovery, and then I'll talk about robustifying it, and then finally conclude with some problems. So let's just go a little bit over the algorithms that achieve this weak recovery notion. Turns out there are many algorithms that achieve weak recovery down to the chaos threshold, not just these long walk statistic ones that I mentioned earlier. There are these spectral algorithms, SDPs, but for us, our starting point is actually going to be the empirical observations about the so-called Bethe-Hessian matrix, which I'll define in the next slide, by Saad Krzyzakala and Zdabarova. So what did they observe? So what is the Bethe-Hessian, first of all? It is this graph matrix, which which has this definition. Okay, and here D is the degree matrix of your graph, and A is the adjacency matrix. This parameter T is a real value from -1 to 1. And I won't be able to get into the motivation behind this graph matrix, but one way to interpret it is a regularized or deformed version of the unnormalized graph Laplacian. So what SKZ observed is that you can actually pick a value of T such that the negative eigenvalues of this Bethe-Hessian matrix are informative in that the eigenvectors can be used to recover the communities. And our theorem verifies this empirical observation, which wasn't known rigorously before in the literature. So we show that there is some explicit T star, which such that the Bethe-Hessian evaluated at T star actually does have at most 2 negative eigenvectors, and one of these negative eigenvectors does contain information about the communities. So here is like a pictorial representation of what we show about the spectrum of H of T star. And our spectral algorithm is based on this Bethe-Hessian, although it's not quite that. I won't get into the construction of this matrix, but we're able to construct this matrix M, which has at most 2 negative eigenvalues, and there's one informative negative eigenvector, which can be rounded into a good assignment. Okay, now I'm going to talk about robustifying this spectral algorithm. So what goes wrong when you allow the adversary to corrupt your input graph? So recall our definition of edge corruptions, where the adversary can arbitrarily add or remove delta n edges. And so we start out with this spectrum H of T star, which we proved in our paper. And the adversary comes in, and it turns out that by adding or removing these edges, the adversary can actually add a ton of negative eigenvalues to the spectrum of H of T star. So this is this H tilde. In fact, the adversary can basically add omega n negative eigenvalues. So how can we actually deal with these annoying eigenvalues? So it turns out that it reduces to the following self-contained linear algebra problem, which I'll explain and then show how how we actually accomplish this problem or solving this problem. So the setting is we get some real symmetric matrix M, which is normalized. It has only a few negative eigenvalues, and there's crucially this Boolean witness, which verifies that the it sort of is a witness for one of the negative eigenvalues. Okay, so the input to my algorithm is some corrupted version of M, this M tilde, where I corrupt it on some principal submatrix and put it on delta n coordinates. You should think of these as being like the endpoints of the edges that the adversary touches. And the goal is to output some constant dimensional subspace U, which is actually correlated with the Boolean witness X. Okay, so we just want to recover something which has correlation with X. And we accomplish this by giving a spectral algorithm that uses some pre-processing steps. Okay, so just as a reminder, so after the adversary comes in and messes with M, we get this M tilde, and the spectrum might look like this. So we're going to clean up this M tilde into this cleaned up matrix M prime, and we're going to run a spectral algorithm. Okay, so ideally, we're able to delete most of these crappy gray eigenvalues. And the idea is that, because the adversary was only able to corrupt on this localized principal submatrix, the new eigenvectors that are introduced by the corruptions also have to be localized. And so might there be a way to detect and delete these localized eigenvectors? And it turns out the answer is yes. There is a win-win situation where either we already have very few negative eigenvalues, or if you look at the set of corrupted coordinates in M tilde and look at, so that's this set S, if you look at the corresponding projection onto the negative eigenspace, then most of the energy in the projection matrix actually lives on those corrupted coordinates. Okay, so if you have few negative eigenvalues and you're done, you can just look at the negative eigenspace. Otherwise, you'll be able to detect where the localized corruptions are by just looking at the projection matrix. And given this, we're going to run the following truncation algorithm. So we're going to repeat this process until we only have a few negative eigenvalues left. So we're going to sample index I with probability proportional to the ith diagonal entry of the projection matrix, and we're going to delete that row and column, just zero it out. And because of this observation on the previous slide, this will delete a corrupted index with constant probability. So we have a good chance of deleting one of the corrupted rows and columns. And we're able to actually prove rigorously that at the end of this process, okay, first of all, it's going to terminate with high probability, and this principal submatrix M prime is only going to have a constant number of negative eigenvalues, and we're not going to do too many deletions. We're going to do O of delta n deletions, where recall delta was our corruption budget. Okay, and because of the fact that the original witness X was a Boolean vector, it's perfectly delocalized, and because of this, you can actually argue that the quadratic form of X against this cleaned up matrix M prime is still negative due to this delocalization property. Okay, and so this proves that M prime is sort of the good matrix, and you just look at the negative eigenspace. Okay, finally, some open problems. So, like I said, this talk is motivated by understanding the brittleness of these computational thresholds when you change the modeling assumptions. So analogously, does the theory of chaos thresholds and other computational thresholds actually change in other semi-random settings? So for example, in looking at worst case graphs with random observations, another problem that is interesting is whether approximate message passing, or AMP, can actually be made robust using some similar type of pruning algorithm. We already know, due to a result of Ivkov and Schramm, which is also being presented at STOC this year, that you can do this robustification of AMP using SOS, but maybe using some type of pruning ideas, you could give a faster, robust AMP algorithm.